All right, so this is chapter 5, and in chapter 5, chapter 6, and chapter 7, we are going to be looking at trig functions. So lots of sine, cosine, tangent, cosecant, secant, and cotangent. We will start out just kind of refamiliarizing ourselves with hopefully what you've learned in a trig class already. I will not be going through this material as though you've never seen it before. It will be more as a refresher. Again, in a pre-calc class, you should have already seen trig. That's Math 175 here at Rio Hondo. And so hopefully you have already learned that material. And so we are going to be kind of doing a brief refresher on some trig topics. So first off, when we are looking at angles graphed on the coordinate plane, this positive x-axis here is called the initial side of an angle, and angles open up counterclockwise, the opposite direction that a clock opens. And that ending angle, or that ending line there, is called the terminal side of the angle, where it ends or terminates. And then the angle in between, sometimes we'll call it theta. That's a Greek letter, theta there. Sometimes we will call it some other variable. Angles can end in quadrant 1, quadrant 2, quadrant 3, or quadrant 4. So again, this is quadrant 1, 2, 3, and 4. Typically, we number those with Roman numerals. And this is an angle in standard position. So these are positive angles in standard position. Negative angles would open up clockwise. So starting here at this initial side and then opening up in a clockwise direction, that would be an angle in standard position for negative angles. There are 4 different types of angles: acute angles that are less than 90 degrees, right angles that are exactly equal to 90 degrees, obtuse angles that are more than 90 degrees, and flat or straight angles, which are 180 degrees. It's a straight line. Again, standard position, initial side, terminal side, opening up counterclockwise. Terminal side, this is called the vertex of the angle, and the initial side opening up in that counterclockwise direction. Some other variables you may see starting in these trig topics that we a lot of times see Greek letters there: theta, phi, alpha, beta, and gamma. Theta, probably most common. Alpha and beta, probably second most common. Phi and gamma, you probably won't see a whole lot. All right. Now, you're probably familiar with degrees around the unit circle, but we will also look at radians. And again, you should have seen that in a pre-calc or in a trig class. And radians are another unit of measurement around a circle. So all the way around a circle would be 360 degrees. In radians, that would be 2 pi. Halfway around a circle would be 180, and halfway around a circle in radians would be pi. And we'll look lower on this page at that in greater detail in just a moment. We can convert back and forth between degrees and radians. If you're going from degrees to radians, you multiply your degrees by pi over 180. If you're going from radians to degrees, you multiply the radians by 180 over pi. So we're going to do a couple examples of these here. We want to convert these degrees to radians. So we're starting with negative 135 degrees, and we are going to multiply by pi over 180. Well, 135 and 180 are both divisible or can be reduced. And 135 and 180, let's see, they have a common factor of, let's try 5 first. Actually, I know I can do more than that. Oh, let's go ahead and start with 5. So starting with 5, 180 divided by 5 is 36. 135 divided by 5 is 27. And so simplifying thus far, we have negative 27 pi over 35. And then I notice that these are both divisible by 3. I'm sorry, I wrote 35. This was 36. both divisible by 3. But there's actually something bigger than that. We can divide both of these numbers by 9. 27 divided by 9 is 3, and 36 divided by 9 is 4. So we have negative 3 pi over 4 as the radians conversion from negative 135. Now, I did this in step by step. If you wanted to do this as 3 at a time and do an additional step to what I did, you could. If you noticed that these were both divisible by 15, 135 and 180 are both divisible by 15, then you could have divided by 15 and done this all in one step. It's really just up to what you see when you're doing the problem. The next one, we're going from radians to degrees, and we multiply by the opposite, so 180 over pi. And we do that in order to get these pi's to cancel out. And 3 and 180 are both divisible by 3. 3 divided by 3 is just a 1 now. 180 divided by 3 is 60. So I have 5 times 60, and that is 300 degrees. And so that is converting those radians into degrees. At the bottom here, it's not showing super well. Let me see if I can zoom in a bit and get this to show a little bit better here. All right, so you can see these angles around the unit circle, and I might need to zoom out just a tad here, in degrees and radians. And I'm going to help kind of color code some of these. I'm also going to show you how to count around the unit circle here. So going in degrees here, counting by 30 degrees, 0 plus 30 is 30. Plus 30 is 60, plus 30 is 90, plus 30 is 120, plus 30 is 150, plus 30 is 180, plus 30 is 210, plus 30 is 240, plus 30 is 270, plus 30, 300, plus 30, 330, plus 30 would be 360. Now we can also count by 45s. 0 plus 45 is 45, plus 45 is 90, plus 45 is 135, plus 45 is 180, plus 45 is 225, plus 45 is 270, plus 45 is 315, plus 45 is 360. So that's how you can count around the unit circle by degrees. We can do the same thing with radians. So if I start out at 0 and I started counting 30, 60, 90, so 30 is pi over 6. So 0, 1 pi over 6, 2 pi over 6, which reduces to pi over 3. 3 pi over 6, which reduces to pi over 2. 3 and 6 reduce to pi over 2. 4 pi over 6, which reduces to 2/3. 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, which reduces to 4/3, 9 pi over 6, which reduces to 3 pi over 2, 10 pi over 6, which reduces to 5/3, 11 pi over 6, and 12 pi over 6, which reduces to 2 pi. So we can count by pi over 6 or 30 degrees, and we're adding 1, 2, 3, 4 all the way around. And just like we did with the 45s, I can do the same thing. So 45 degrees is pi over 4. I can go ahead and add pi over 4. So 0 plus pi over 4 is 1 pi over 4. 2 pi over 4, which reduces to pi over 2. 3 pi over 4. 4 pi over 4, which is pi. 5 pi over 4. 6 pi over 4, which reduces to 3 over 2. 7 pi over 4, and then 8 pi over 4, which is 2 pi. So we can count around the unit circle with those radians and get those hopefully memorized. You should have this unit circle memorized. But if you don't at this point, you need to get it memorized. I'm going to color code these here in just a second. All of the 30-degree angles, all of the ones with a 6 on the bottom, we kind of group together, and we'll see in the next section how those get grouped together even more. So let me actually just box each of these. So those are all of those 30-degree angles. And then all of my 45-degree angles have a 4 on the bottom. And then all of my 60-degree angles have a 3 on the bottom. Oops, 240. And there we go. All right. So that whole will hopefully help you remember all of those angles around the unit circle and be able to count around the unit circle well. Now we are going to talk about coterminal and reference angles. Coterminal angles are angles that have the same start and the same end. So their initial side and their terminal side land in the same place. Reference angles are not the same. Reference angles are used to evaluate angles that are hard to evaluate. So coterminal angles, you can add 2 pi or add 360 as many times as you want. That's what that k means, where k is an integer here. Or we could subtract 2 pi or subtract 360 as many times as we want, and that would give us a coterminal angle. So in these first couple examples here, it says find a positive coterminal angle less than 360 or 2 pi. 17 pi over 3. If I divide 17 by 3, that's a little bit more than 5. It's about 5.7 if you divide on your calculator. So I want something less than 2 pi, and that's already more than 5 pi. So I can subtract 2 pi as many times as I want. Well, 2 pi is, with a common denominator, I can multiply by 3 over 3 to make a common denominator. And then I have 17 pi over 3 minus 6 pi over 3. And if I subtract, I get 11 pi over 3. But 11 pi, or 11 divided by 3, is 3.3. That's not less than 2 pi yet. So I need to subtract by 2 pi again. So 6 pi over 3, and 11 minus 6 is 5 pi over 3. 5 divided by 3 is 1.7. That is less than 2 pi. And this is an angle on the unit circle. And so this is now a positive coterminal angle to 17 pi over 3. That is less than 2 pi. So we subtracted 2 pi in those situations here. And if you had noticed that you were going to need to do it more than once, you could have subtracted from the very get-go by 4 pi instead of 2 pi. But we can also add 2 pi or 360. And if I add 360, then if I add it one time, I end up with, let's go ahead and calculate that. Let's see. We get negative 495. But we want a positive coterminal angle less than 360. Well, this is not positive yet. So we can keep adding 360. And if you notice that you're going to need 3 360s, then in one step, you could multiply 3 times 360. But if you don't notice that, we can just add 360 at a time until we get to something that we need. So when I add that again, I end up with negative 135. And though that is the number portion less than 360, it is not positive. So I need to add 360 again. And when I do, I end up with 225. And so 225 degrees is a positive coterminal angle to negative 855. All right, and the last topic in this section is arc length and area of a sector. And what these two formulas here are telling us about is the length of the arc on a circle. So if you have a circle and you know the size of the angle here, and you know the radius of the circle, you can find the length of a sector of the circle by multiplying the angle times the radius. So that's this formula right here, the radius times the angle theta. And that gives us the length of the sector. And then we can find the area of that sector by multiplying 1/2 times the angle times the radius squared. So let me zoom in. I know on your paper, hopefully you can see it, but right here, it's a little bit hard on the screen. This is a 2 right here. So finding the area of this entire highlighted yellow sector here, I would multiply the angle times the radius squared times 1/2, and that would give me the area of this sector. Okay. All right, and that brings us to the end of 5.1.